All right, it's my pleasure to introduce this week's speaker, Caleb Jonker from Charles University, who will speak to us today about untwisting generalized Taylor-Ricci flow. So please, Caleb.
Okay, so thank you for the invitation. So yeah, this is a project that comes out of my PhD thesis with Marco Gualtieri as my advisor, and uh, I called the title "Untwisting Generalized Taylor-Ricci Flow" for reasons um, which we'll see. But basically, the goal is to give uh, a, a reformulation of the generalized Taylor-Ricci flow. Um, Uh, so I'll start by giving a little bit of background for those who may not know. Um, so generalized Kähler geometry came out of physics in the 1980s with a paper of Gates, Hall, and Rocek. And they said that, well, without giving any of the physics background, generalized Kähler geometry arises from supersymmetry. In particular, it comes from n equals 2, comma 2 supersymmetry, supersymmetric sigma models. And what is it? Uh, you have a manifold, a Riemannian metric, and a pair of complex structures, which are actually Hermitian with respect to the metric. And they satisfy, this is a metric, they satisfy the following integrability condition. So dc plus equals dc of omega plus equals minus dc minus of omega minus, where dc plus, so for each complex structure you get a del bar and a del operator. Oops. If you combine them in this way, you get dc plus and minus. And omega plus minus are just the Hermitian forms. So I'll call this particular three form H, and we'll also require that dH is 0. So this is generalized Kähler geometry, and in particular, in quantizing the theory, you're led to a particular flow, which in physics they call renormalization group flow. And as far as I'm aware, it was only studied in the bosonic case uh, in physics, where they found generalized Ricci flow. And then much later, Jeff and Tian, uh, they discovered that generalized Ricci flow extends, which is a flow of a Riemannian metric, uh, and perhaps a B field, extends to a flow of generalized Kähler structures, which is written in this way. So in particular, one of the complex structures, the I plus is fixed, while the I minus flows by some one parameter family of diffeomorphisms. And let me just say what h squared is. H squared is a symmetric two tensor, just given by you contract into the H and then you pair using G. And theta is minus dc of omega after I. And of course, there's one for I plus and one for I minus. And this is called the Lie form. So I'll just note this, you probably observed that this flow is asymmetric because it fixes one of the complex structures, but this, of course, can be corrected just by doing a gauge transformation by a one parameter family of diffeomorphisms. But I'm going to prefer to work in this particular gauge. So now, so this is mostly a story of things that happened in the 80s, but in between then and now, Hitchin introduced generalized geometry. And so what is this introduced by Nigel Hitchin? And the generalized complex structure. What is it? It's an operator on this bold Tm, which is the tangent bundle plus cotangent. Which squares to minus 1. And it's compatible with the natural structures that exist on bold Tm. So there are two of them. You have a split signature metric. And also a bracket where x, so I should say x and y are vector fields and c and eta are one forms for this entire talk. And you take the Lie bracket of the vector fields and this non-skew operation on the remainder. And then you can twist this at y at x h by a three form. H, a closed three form. And what it means to be compatible is that, well, J has plus or minus I eigenbundles, which we'll call L and L bar, and we want them to be involutive with respect to this bracket. And that in particular, so these structures, the metric and the bracket, together give the structure of a Courant algebroid. Which is well, it seems like a strange object when you first encounter it. But in particular, if you take the one of these involutive subbundles, it's called a Dirac structure, and here you really get a Lie bracket because this thing is isotropic, and so you get a Lie algebroid. So I'll just give a few examples. If I is complex structure, then you can take the following combination. On T plus T star. And this will give you a generalized complex. And there's a slight modification you can do to this complex structure, which is that you can add something in the top right corner. And this thing has to be a bivector. And in particular, this combination is integrable precisely when you have a holomorphic Poisson structure, which is produced in this way. So, okay, so that's my second example. And then the only other example that I'll give is if you have a symplectic form. Then you can, again, produce a generalized complex structure. So the reason that I'm telling you about generalized complex structures is because it's a theorem of Gualtieri that generalized Kähler geometry is equivalent to a pair of generalized complex structures. Of commuting in particular. Such that you have a positive definiteness condition, which looks like this. And okay, the equivalence is given, I'll just give you the explicit formula. So you just have to combine all the tensors in the right way, and by what seems like luck, you get a generalized Kähler structure. Now I'll say maybe a slightly more conceptual way of understanding this equivalence, which is given by looking at the Dirac structures underlying JA and JB. So if I draw a picture of the complexification of T, Then because JA and JB commute, it breaks into four pieces coming from LA and LA bar and LB bar and LB. And I'll call these L plus, L minus, L plus bar, and L minus bar. And the correspondence is given by noting that if I project from TM onto TM, in particular, this projection gives an identification of L plus and L minus with T 0, 1 of M with I plus or I minus. Okay, so we'll use this conceptual relationship later on. But there's one more thing that I want to just observe here, which is that for any generalized complex structure, if I look in the top right corner, you get a Poisson structure. We saw this you see it in both of these examples. And here you get a non-degenerate Poisson, and here you get the imaginary part of a holomorphic Poisson. But in here, we're going to use these Poisson structures, which I'll call pi A and pi B. And these are real Poisson structures.
Can I ask a stupid thing?
Yes.
So when you write down generalized scalar in terms of classical data, there is an asymmetry coming from the fact that you have to choose H to be either minus DC plus or but here when you write in terms of generalized general geometry, there is no difference between JA and JB. So what makes the difference in the classical case?
I
That you
think
choose an orientation or what?
I think what you're maybe noticing is that there are two ways to embed Kähler into generalized Kähler, which I should maybe have remarked on. Um, you can either, so why is this generalized Kähler? It's because if you take I plus equal to I minus, then the condition is just becomes that dc of omega is 0 or d omega is 0. So you get something Kähler. But you can also take I plus to be minus I minus. And that also gives you a Kähler condition. Um, uh, I'm not sure if that answers your question or not.
I'm not sure, but thank you.
Um, yeah, okay. So in addition to these real Poisson structures, there are also holomorphic Poisson structures lying around. So these were observed by Hitchin. GK structure comes with holomorphic Poisson structures. And you get one for each of the complex structures. So I'll call them sigma plus minus. And these are minus 1/4 IQ plus IQ, where the only thing that changes is this complex structure I plus minus. So they have the same real imaginary part. And the imaginary part is given by 1/2 I plus I minus G inverse. And again, I want to give a slightly more conceptual understanding of where these holomorphic Poisson structures come from, and this is due to Gualtieri again. Uh, uh, and he showed that these holomorphic Poisson structures can really be thought of as pullbacks of the Dirac structures coming from JA and JB. So this is a diagram of Dirac structures. And what I want to note about it is that while these LA and LB and LA and LB bar, these are Dirac structures with some twisted Courant bracket, twisted by this three form H. But L sigma plus and L sigma minus are not. They're Dirac structures with respect to H equals 0, the untwisted Courant bracket. And this is also true for gamma pi, the graph of pi A and the graph of pi B. These are untwisted Dirac structures. And in some sense, the main theorem in this talk is built on a silly observation. Which is that if I take pi A plus pi B, I get omega plus inverse. And if I take pi A minus pi B, I get minus omega minus inverse, just looking at their form. And so in particular, the triple, let's say L sigma plus, and the graph of pi A, and the graph of pi B encodes the generalized Kähler structure, meaning that I can recover it from these three Dirac structures, these three untwisted Dirac structures. So that's why I call this an untwisting of generalized Kähler geometry. And what I'm going to do is I'm going to describe the generalized Kähler-Ricci flow in these untwisted terms. So let me, at this point, state the theorem. So generalized Kähler-Ricci flow is given by the action of a Courant derivation which is called R minus plus. And this is, so if you don't know what a Courant derivation is yet, I'm going to explain it, but for now you can just think, because it's true, that it's a vector field on some space. And this vector field is going to act on the triple L sigma plus, the graph of pi A, and the graph of, I'm actually going to take minus pi B in this case. So now for the rest of the seminar, I'll explain what these words mean. So maybe it would be an okay time to stop if there are any questions about the statement or about the setup.
Well, I guess when you say vector field, you mean like on some infinite dimensional space, I guess.
No, it's really a vector field on a finite dimensional space. It's the space which is the total space of of TM, bold TM.
Oh, I think I know what you mean. Okay, yeah, okay.
If you take, yeah, yeah. In any case, I'll explain it, but
Okay.
that's the next thing. I don't know. Are there any other questions? Okay. So the first thing that I need to explain is symmetries of Tm.
Sorry, can you briefly comment on how you recover the full general scalar structure from the triple? Because I mean, sigma
Oh,
plus is given by a commutator, right? So is it
uh, yeah, let me, uh, yeah, I guess I didn't explain that very clearly. So I have omega, I can recover omega plus and omega minus. Um, and from here, all I need is one of the complex structures to recover the rest of the data.
yes?
And so in here, in L sigma plus, this is why I say it's a stupid observation, is because L sigma plus, well, it has inside of it a complex structure. That's part of the data of a holomorphic Poisson, is a complex structure. So I just have in there I plus. So you
Okay.
actually don't even need the two tensor. This is more data than you need.
Okay, so you're implicitly assuming that you have the complex structure of I plus in the manifold, which comes from L sigma plus. Is that what you're saying?
Yeah, so let me say more. L sigma plus, so that's L sigma plus is supposed to be the plus I eigenbundle of the generalized complex structure, which which is encoded by the which comes from the holomorphic Poisson. So it's this example here.
Okay.
So you can write out what it is actually. Uh, it's basically the graph of sigma plus t 0, 1 of I plus. So in there you have the complex structure in particular.
Okay. Thanks.
Uh, so let me say what symmetries of current algebroid are. So this bold Tm, it's a metric vector bundle, so it has some Atiyah algebroid, which projects onto Tm, sits in this exact sequence. And what this is just that these sections of the Atiyah algebroid, what are they? They're vector fields, as I was saying, on the total space of Tm, which preserve the metric. And these are what I would call infinitesimal symmetries. Or maybe derivations. Now, just a remark that there is no natural splitting of this sequence. So we can't identify, in an obvious way at least, we can't identify the Atiyah algebroid with vector fields and sections of SOTM. And yet you have something which it looks like a splitting at least, which is the Lie derivative. And so this actually does give you what you need. So sections of T are given by pairs Z phi. Z is in section of Tm, and phi is in SOTM. And these have to act on sections of Tm. And the way that you do it is you by Lie derivative and then by just plugging in to the SO part. I think I want to actually have a minus sign here. And the key thing is that this pair Z phi is also a symmetry of the bracket precisely under the following conditions. If you need, so first you want to notice that this SOTM, well, it should be wedge 2 of Tm, which includes bivectors and homomorphisms of the tangent bundle and two forms. And this thing is a symmetry precisely when phi, which I'll now call B, is a two form. And Lz of H is equal to D of B. So these symmetries are what we're going to use to drag around, these vector fields are what we're going to use to drag around this triple of Dirac structures. And
I mean, for principal bundles, there is no such a lifting. So I guess you're using that you're in a specific splitting, or
yeah, exactly. I'm using precisely the fact that this is not any metric bundle. It's a very special one. Yeah, so somehow from the point of view of the Courant algebroid, this is not really a very natural description, but nevertheless, it's useful.
okay.
So the way that we're going to encounter these symmetries comes from generalized connections. So if V is now a vector bundle, we're actually going to take a line bundle eventually, but it can be a vector bundle for now. So a generalized connection is a differential operator, which allows you to differentiate in the directions of bold T. And what this means is that it satisfies a Leibniz rule. Where only the vector field part acts on functions. And what this means, since only the vector field part acts, means that you can, in particular, there's a part in here which is a tensor. And you can split this into the part which eats vector fields and the part which eats covector one forms. And this one is a connection, a usual connection on V. And this one is a vector field valued in endomorphisms of V. And if V is a line bundle, it's just a vector field. Now, you can take curvatures of these generalized connections. Using the usual formula, where we now have to put the courant bracket here. And the nice thing about these curvatures is they actually live in sections of the Atiyah algebroid tensor endomorphisms of V. Or again, in the line bundle case, just sections of the Atiyah algebroid. And moreover, there's a nice Bianchi identity, which says that precisely that R is a derivation of the bracket. So to simplify the statement of the Bianchi identity, you have to assume that V is a line bundle in this case. So we really get a symmetry of the whole thing, the Courant algebroid. So let me just say how do you compute what the curvature actually is. Well, it has a very nice formula where you take the vector field part and you take the curvature of your connection, and then you have to add the contraction of the vector field with H. This is what the symmetry that you get. So now, I have to speed up. Okay. So I'll go to a specific example, which is generalized Chern.
By the way, sorry, Caleb. I mean, it's sort of okay if you go over, I guess. I mean,
Oh, okay.
people will probably leave, but it's being recorded, so it's not
Okay. So do you have a suggestion for when I should try and stop or?
Uh, I hesitate to answer that question. I don't
Okay.
know.
I'll just try and go.
I'm just saying maybe you don't have to blitz is all I'm saying.
Okay. Sure. So generalized Chern connections. So if I have a complex structure, then I'm sure most of you know that if you have a holomorphic vector bundle and a Hermitian with a Hermitian metric, then there's a unique connection which preserves H and satisfies that 0, 1 part is the Dolbeault operator. And the same is true in the generalized complex, or a similar thing is true in the generalized complex setting. If you have, now you don't need a holomorphic vector bundle, but you need a generalized holomorphic vector bundle, which is going to be a L connection. Oops. A flat L connection on V, and again, a Hermitian metric. Then you get a unique generalized connection, preserving H with the L part equal to del bar. This generalized holomorphic, generalized Dolbeault operator. And in this case, we know even more about the curvature. Because this generalized connection came from a flat del bar, a flat L connection, it tells you something about the type of this curvature, and what it tells you is that R is a symmetry of J, the generalized complex structure. So now let's move to something even more concrete, which is the particular line bundles.
Caleb, I might be confused. So
Okay.
in the case of the curvature of a generalized connection, I guess you identify an element in lambda 2 of E with an element of Atiyah using the pairing, but here, what is the thing that you choose for?
This thing is not in wedge 2 of E.
It's not tensorial, right?
It's not tensorial. I would argue it's better than that. It's a symmetry. It's in the Atiyah of TM. So does that answer the question?
And no, I mean,
Um,
my question is, what do you mean by the Chern connection below to be a symmetry of J?
ah, yeah. What I mean is, um, in particular, if you take, so it has two slots, and there's many ways of thinking about it, but um, so one of them is that, okay, so how do I see this connection between R and a derivation, a section of the Atiyah algebroid? Well, maybe what I should have said is that R looks like this for some derivation. In particular, R is tensorial in the last slot, in the second slot. So you can
Okay.
identify it with something of this form. It's a derivation, and then what I'm saying here is that D commutes with J.
But here
Another
is
way
just
of
the,
seeing it is that if you plug something in L and L bar into R, you get 0. Sorry, no. If you plug two things in L into R, then you get 0.
yeah, but I guess my point is L here is isotropic, right?
Yes.
So what does, I mean, previously you used the pairing in the Courant algebroid to define D. So what do you use to define D now?
Uh, it's the same. It's the same definition.
Okay.
D, yeah, R. It's what I wrote above. I think what you're noticing is that R, if I restrict R to L, then I get 0. Or to wedge 2L, maybe. So this is
Okay.
another
So
way of saying the
I,
same statement.
So you are extending this to the full E. Okay.
Yeah. Yeah, this thing is not, yeah, it takes sections of TM and two sections of TM, bold TM.
Okay, now I understand. Sorry. I
Okay.
understand now. Sorry.
No. Okay. Okay, so yeah, the concrete setting where we're gonna find find these line bundles comes from the spinors in generalized geometry. And okay, so what are they? Well, the Clifford algebra of Tm acts on differential forms. And it does so in this way. If you take a vector field and a one form on a differential form, you contract the vector field and you wedge the one form. Then you can check that this action satisfies the Clifford relation. And in the presence of a generalized complex structure, actually, let me say one more thing before I add a generalized complex structure, is that there's a very nice operator on the differential forms, which is the Dram operator plus wedging with H. And I say a nice operator because this operator has the property that it generates the Courant bracket. Um, so what you'll notice is this operator doesn't have, it's not Z graded anymore. It's only Z2 graded. So you lose a grading, but we're gonna see that there's more than enough gradings around. In particular, in the presence of a generalized complex structure, the differential forms, you have to complexify them now. They decompose into many pieces. Uh, where this decomposition is really given by the action of J. And we'll call at one end you have a line bundle called K, and at the other end you have K bar. This decomposition has a symmetry by complex conjugation. And in particular, if I act by powers of L, I move around. So if I go from K to one slot over, this is just L bar acting on K, which using the metric can be identified with L dual tensor K. And now this operator dH decomposes into two pieces, del plus del bar, and del bar is going to move you to the left, and del is going to move you to the right. And what you find is that this del bar gives a generalized holomorphic structure. Okay.
So here K is the canonical bundle of the generalized complex structure, right?
Yeah, thank you. I should say that. Canonical. bundle of J. So it's precisely the bundle which is killed by L. If I act by L, I get 0. Now, any Hermitian metric on the canonical bundle has a nice expression, or it can be expressed in a nice way. Actually, let me put this on a new page. And it uses the fact that the spinners always have some pairing. And in this case, the pairing takes you to the top forms. So any Hermitian metric H on K takes the form H alpha beta. We use the spinner pairing, which looks like this. Take alpha, you wedge it with the complex conjugate of beta transposed. Then you take the top piece. That's just the spinner pairing. And then you divide by mu for some volume form. And using this Hermitian metric, the generalized Chern connection has a nice form. You can decompose it into its pieces. And the vector field part, which I've called x pi, is known as the modular vector field. Of pi, where this pi is the Poisson structure coming from J. So let me just say what the modular vector field is. X pi acting on F is Lx L. You take the Hamiltonian vector field of F, and you act on mu, and then you divide by mu. So this thing has been studied by many people in the Poisson community, and it gives you, in particular, the modular class of a Poisson manifold. But from our point of view, we're just going to use this as a computational tool. This allows you to compute X, the vector field part of a generalized Chern connection.
Sorry, Caleb.
What is Nabla?
Oh,
Sorry?
No, what is Nabla?
What is
Nabla
Nabla?
without the bar.
Yeah, that's a good question. And Nabla is some connection, which I will not say what it is in general, because I don't actually know. But yeah, I guess all I'm saying is that the vector field part of the generalized connection has a nice form.
Okay.
In some sense, the Nabla part of the generalized connection is less natural because if you change your splitting, the connection will change.
and
Yeah.
is there a general expression for the first Chern class of this line bundle, like in terms of the like classic first run classes or something like that
Um,
of the classical complex structures?
I think what you might want to say is that if you take the curvature of this connection, then it gives you something which you might want to call a generalized Chern class. Uh, um,
No, but I mean, it is ultimately a classical line bundle over the original,
yes, and
but maybe it's not holomorphic with respect to either of the complex structures or something, or
yeah, in this case, there's no complex structures. All I have is a generalized complex structure.
oh, well, okay, but ultimately, of course, we're going to use, consider the generalized Kähler case, and then you will, right? And
Yes. Um, yeah, let me do that now. I don't know if I have an immediate answer for your question,
okay. Yeah.
but it's an interesting thing to think about. Uh, so yeah, let's move to generalized Kähler geometry. So in generalized Kähler geometry, you have a bigrading now. So I'm going to draw a diamond. And here we're going to have canonical bundle of JB and the canonical bundle of JA and their complex conjugates. And we have some other pieces as well. And an important thing about this diagram is that uh, the different pieces, the little Dirac structures that we have lying around, all act in a different direction on this diagram. So let me draw this way. In particular, if I act in the Clifford algebra with L plus, I move up and to the right, and L plus bar moves in the other direction, the opposite direction, and then L minus and L minus bar take you this way. So one thing that you might notice is that if I go from KB to KA, this is acting by wedge top of L minus, which is just the canonical bundle of I minus. So we get an identification. Ka is equal to K minus tensor KB. And also you can write something like K plus tensor KB bar. And another thing about this identification is that this entire diagonal has a holomorphic structure coming from decomposition of this DH. DH now decomposes into four pieces. And we use the one that goes in this direction. Oh, sorry. Oops. That's not the direction I want. we use the one that goes in this direction, we get a holomorphic structure on this bundle. So we get an I plus. So this is I plus holomorphic. And this whole identification is an I plus holomorphic, identification of I plus holomorphic line bundles. And similarly, this identification, which comes from, maybe let me use a different color. Which comes from this diagonal. It's an identification of I minus holomorphic line bundles. Now the thing that I really want to use is I want to get to a specific module and produce its generalized Chern connection. And so what you'll notice here is that Ka has an La module structure, and Kb has an Lb module structure. So you might ask, what kind of structure does K minus have? And it has neither La nor Lb, but you can use the diagrams that I drew earlier. Let's go back to them. These diagrams to show that, whenever you have an La module structure, you have an L sigma plus module structure. And similarly, you have an L sigma minus module structure coming from these maps. And whenever you have an Lb module structure and an Lb bar module structure, you get L sigma minus. So what we do is we use the L sigma plus module structure on Ka and Kb to produce an L sigma plus module structure on K minus. K minus an L sigma plus module. It's also an L sigma minus module, but we're not going to use that one for some reason. And K plus is an L sigma minus module.
So when you say model, you mean by action with the Dorsman bracket or no? The action is algebraic, or you mean some differential operator?
It's a differential operator. Yeah, I mean there's a flat L sigma plus connection. That's what I mean. Maybe I should say that. In the sense of Lie algebroids. And okay, so again, it's a generalized holomorphic bundle with respect to a certain generalized complex structure. In this case, the one coming from the holomorphic Poisson structure. And so we can produce generalized Chern connections on both K minus and K plus. And nabla plus minus on K plus. And generalized Chern curvatures. And using this machinery this proposition and other machinery, which I won't get into, you can write down what actually these curvatures are. They take this form where this is the Ricci-Bismuth. It's the Ricci form for the bismuth minus connection, which is the metric connection with torsion minus 1/2 G inverse H. And similarly, R minus plus minus is 1/2 theta plus sharp minus theta minus sharp minus rho bismuth plus.
And here the splitting is the one given by the generalized scalar structure, right?
Yes, that's right.
And so is this kind of saying that these Lie vector fields are they should somehow be the modular vector fields of the Poisson structures?
It's not quite saying that because oh no, sorry. Yes, it is saying that.
Some combination of them, or
These are a modular vector field for yeah, the imaginary part of the holomorphic Poisson structure.
imaginary part.
That's right. Yeah. I mean, if you go back, so we need to compute to produce it as the modular vector field of a Poisson structure. This Poisson structure came from whichever J we happened to be using. And in this case, we're using L sigma plus on K minus. So you look at the real Poisson bivector, which is the imaginary part of this of sigma plus, and that's what gives you the modular vector field.
But the vector fields which appear in R plus minus and R minus plus don't have one more derivative than the one which appears in the generalized connection.
Sorry, actually, before I answer that question, I just have to correct myself because I said something incorrect. Yeah, these are not the modular vector fields for any bivector, because in order for that to happen, we needed to start with a canonical bundle and take its generalized holomorphic structure. Here, what we're doing is slightly different. I'm starting with something that is actually a canonical bundle, but I'm taking an L sigma plus module structure, a holomorphic structure, for a different generalized complex structure. So these things are very closely related to modular vector fields. And in fact, they're combinations of certain modular vector fields, but they're not themselves modular vector fields.
Huh.
Okay. So did you have a question, Mario, or was...
Yeah, but doesn't make sense.
Okay.
So
So that's pretty much all I wanted to say. I'll just reiterate the theorem, which is that the action, if I take R minus plus, which is this derivation, and I act on this triple L sigma plus graph of pi a and the graph of minus pi b gives generalized Caylor-Ricci flow. Now, hidden in here is something kind of important, is that this thing, because it came from an L sigma plus module, it's a symmetry of L sigma plus. So it actually doesn't do anything to L sigma plus. And in particular, it doesn't do anything to I plus. So this gives, in here, you can clearly see that the holomorphic Poisson structure is fixed by R minus plus. And similarly, if you wanted to work in the other gauge where you have I minus fixed, you could take the action of R plus minus on L sigma minus, graph of pi A, and the graph of pi B. And that gives the I minus fixed generalized Caylor-Ricci flow. Okay, I'll stop there.
All right. Thanks, Caleb. More questions? I guess I wonder if you'd mind. Can you just go back to my question about like the relationship of those vector fields to the modular vector fields?
Yeah. Okay, so let me maybe say how I actually computed this. I've kind of hidden what I did. To start with, I computed the so you really have a whole soup of connections and curvatures lying around. In particular, each KA, and KB, these have curvatures, which I'll call RA and RB. And these ones, I don't remember the formulas. They're in my thesis. But these ones in particular have modular vector fields for pi A, pi B, and modular vector field for pi A, and something else, which is the curvature of some connection. Now, so these ones these modular vector fields you can really compute just using like the Riemannian volume form. UG gives you a computation of what these modular vector fields are. And then using these connections, you can use curvatures plus minus. So again, I'm using this diagram. Where'd it go? Here. To produce L sigma plus and L sigma minus generalized Chern curvatures on Ka and Kb. These are again different curvatures, which has another formula which I don't remember. RB plus minus. And you take some combination. To get K minus, you just take a combination RA plus. Let's say if I wanted to compute R minus plus, I think that was the one. What would I do is I would take RA plus and I would subtract RB plus. So that's how the computation goes. Plus RB. Oops.
Can you say again, to obtain the curvature RA from KA, you regard KA as a generalized holomorphic lane bundle with respect to which generalized
With
computation
respect to
theorem?
LA, the natural one.
Okay.
Yeah. So RA and RB are the usual generalized turn on canonical bundles. So yeah, part of the history of this project is that one of the goals was to try and show that the generalized Caylor-Ricci flow could be expressed in terms of RA and RB. And I tried to do that for a long time and never figured it out. Um,
Well, but didn't you? You just had to combine them, right? I mean, isn't that the upshot?
yeah, I mean, I guess in a sense this is a way of producing it from RA and RB, but it's uh, more involved than I expected it would be.
Sure. Maybe if we can, yeah. Let's thank Caleb one more time and then I'll turn the recording off. So yeah, thanks.